I have the pleasure to have Francis Albert with us, who will talk about turbulence and magnetic perturbations in Tokamak's Navy Accelerator suit.
Actually, only in Tokamak, actually. Yeah.
Okay. Welcome, Francis. And well, at first, if you could tell us a little bit more about yourself and the experiences that led you to fusion, what motivates your career, what you're planning for the future.
Mm-hmm. Okay, yeah. Okay, Alexis. Okay. So I was a master's student in Fusion AP program, and like before doing my master's program, I was actually an engineering student in electrical engineering. I came to know about nuclear fusion like during like online search, and then I got interested into it. After that, I just like came into contact with some of Indian friends who are already in this master, and with their guidance, I enrolled in this Fusion AP master. After enrolling, like I had this interest of doing research in turbulence. Like so, I did some internship in like my first year was in Nancy in University of Lorraine. Like during my first year, I did an internship in turbulence, and then again I did another internship in Spain in CMAT, where I also studied like turbulence, but in a like a experimental side. Like this two internships like helped me to get some exposure in turbulence, which also helped me to get a chance in like doing a master's thesis in IPP caching. So where I actually had this like all my fundamentals in turbulence like brushed up, and which helped me to like to understand more about this turbulence topic and what are the how we usually study this turbulence using the gyrokinetic tool and what's the theory behind the gyrokinetic tool, everything. And then like somehow like I can say like I know like what direction I want to go in this field. So in future I like to study turbulence in accelerators like during my PhD, and then understand how there are different kind of turbulence, like how each kind of turbulence can be optimized by optimizing the magnetic geometry of accelerators. So that's like a kind of goal for me currently. I think Alexis, I think you are in mute now.
Apologies. So, could you tell us a bit more about the field? Who are the major players? Who are what groups are working on what, and who would you like to work with? Hello. Hello. Hi. Francis, can you hear me?
Yeah, so I couldn't able to, like I can hear you now.
Okay. So I was just wondering if you could tell us more about this field and what's the what are the big problems that are being tackled today, and who are the major players in this quest?
In the field of turbulence.
Yes.
Okay. So major players. Okay. So I'll tell what I know. So usually like we know this like the turbulence is one of the major constraints for achieving a good confinement. So they're like any institute like they have this some kind of focus in turbulence research. So I can't figure out like this particular institute is good or bad or like primary focus. But I can say like there are different kinds of tools that are developed independently by different institutes. So each code has its limitations and advantages. So which means, and also many of the codes are open source. We can, so anybody who has this, who knows how the like has the gyrokinetic knowledge can usually use the code and use it. So yeah, it basically depends on the independent research group's interest. Like there are many different ways each group will use these tools. For example, stellarator groups will use this to study stellarator optimization. But in Tokamak, we have like variety of researchers. Like in this case, how they like ELM suppression affects the turbulence and how this LH transition is happening. So it depends on the each individual group's like aims and ideas, what they want to achieve.
So you've mostly been working with gyrokinetic models, is that right?
Yeah.
Could you explain us in simple words, if that's possible, what a gyrokinetic code is?
Yeah, I can explain. So analytic description of plasma. So it's basically it has this like a particle distribution function, and using that we can find the evolution of a species in XV, like in phase space. So and using that, what we did is we just somehow average that function, like reduce that kinetic description to describe the turbulence process. For turbulence process, we don't need one particular dynamics of particles, and that is the particle dynamics around the guiding center, which means the gyro ring that particle forms when it flows in a magnetic field. We don't want this particular information in the kinetic description. So what we did is we just remove this information from the kinetic description, and then we get a gyrokinetic model. So gyrokinetic model is just kinetic model where the information about the particles motion around the guiding center is removed. So we get this gyrokinetic model. So this gyrokinetic model can be used to study turbulence, like also many things, but major thing is the turbulence.
And so what kind of turbulence are you particularly interested in?
Currently, I don't know which type of turbulence I'm currently interested in, but many people say it is the ITG and ETGs, which are the two dominant. Okay, what is ITG? Okay, ITG is ion temperature gradient turbulence, which is mainly driven by ions, and ETG is like electron counterpart for ITGs, and depends on the mission. Like some mission can be ETG dominant, some mission can be ITG dominant. Like these two are the like most dominant turbulence, which causes this transport in particle and heat. So they say like this are dominant thing. But currently I don't have any interest. It depends on like because ITGs are easy to simulate when compared to ETGs, which I will talk about later. So many people when they want to start, they can start with ITGs turbulence. They'll start studying ITG turbulence.
ETG is more difficult because you need more resolution.
Yeah, because the electron scale is yeah exactly.
You need more resolution in velocity space or in normal space, both?
Like you basically need velocity like XYZ. I don't know, but velocity doesn't depend on whether it's ITG or ETGs. But for XYZ, it matters because okay, so the G again coordinates here is like it's similar to the Boozer coordinates, so where we have X is the radial coordinate, so it selects the field flux tubes or the flux coordinates. So that is also need to be resolved in electron scale. And then there is a alpha coordinate, which is similar, which is mapped to Y, and that selects the field line in this flux tube. So that also is in terms of should need to be in terms of electron resolution. And Z coordinate is fine. Z coordinate doesn't depend on the ITG or ETG. It depends on the specific magnetic geometry equilibrium that we use for simulation. For example, it depends on the machine or the equilibrium that we use. So X and Y depends on the resolution or the turbulence that we want to simulate.
So if you're ready, would you take the floor and give us a quick general introduction to the topic that you developed and what you would like to be focusing on?
Yeah, sure, Alexis. Yeah. So, okay, so like this is a slide, like a overview of what we are going to see today. So everybody, like I think, like this for the H mode plasmas, we achieved this in Tokamak. I have this high confinement, but this high confinement mode has one problem because due to high pressure that is created inside the plasma, there is some MHD activity is triggered, which is called as ELMs. So this is called as Edge Localized Modes, and this Edge Localized Modes just like it's like intermittent burst, and which just expels this, like which reduces the pressure from the plasma by having this intermittent burst onto the plasma walls. But the problem with ELMs is like when we want to scale this H mode to like a bigger reactor like ITER or DEMO, where the H mode we can achieve, but the pressure will be so much. So the ELMs will create so much of um, disruption, not disruption, like so much of burst, intermittent burst, that walls can't withstand. So we have to somehow reduce this uh, ELMs or like control them. Either we can mitigate them, or maybe by mitigating means we can make the each burst less um, less damage to the walls by reducing the amount of pump out happening, or we can completely suppress the ELMs. So one of the ways to achieve this two thing is use the magnetic perturbations. So that is the third thing here. So what happens is like we have some external coils around the top, and this external coil is used to create a magnetic perturbation, which means they carry a current, and this current is small, and this change in magnetic field will create a plasma, some kind of plasma response. So plasma response is somehow, we don't completely understand how the plasma response actually happening. But the thing is, the output is somehow the ELMs is suppressed or mitigated. But during this process, we achieve something. So that is called as density pump out. So what happens is, as I said, like to the ELMs will reach, like ELMs will be triggered when the plasma reaches certain pressure. So pressure is nothing but temperature times density. So what happens is when magnetic perturbation is applied, this density pump out is happening, which in turn reduces the pressure of the plasma. So thus reducing the ELMs, like thus reducing the, like thus never plasma never reaches the pressure threshold needed for ELMs. And then one thing is we doesn't know what causes this density pump out, like what's the mechanism that's behind the density pump out. How can we quantitatively predict how much density pump out is going to happen? Because, and people know that this density pump out is happening because of turbulence. So but we doesn't know which kind of turbulence is happening. Like we doesn't know quantitatively, we can't predict how much density pump out can happen. So that's the main thing. And next thing is, other than density pump out, the people also started to observe different kind of observation, which I will explain later. That is also caused due to turbulence. So the main goal is, so we know that these are the two reasons that ELM suppression is happening, and this is caused due to turbulence. Like turbulence plays a major role. Once we understand the link between the turbulence, density pump out, and ELM suppression, we can effectively suppress ELMs in the future reactors. We can effectively design the external coils, like the magnetic perturbation, to efficiently suppress the ELMs. So that's the goal. So how to study turbulence? So one of the like efficient or like the efficient way to study turbulence is to use gyrokinetic simulation, because gyrokinetic theory can be used to study turbulence. So we use the tool called Ghent 3D, which is based on gyrokinetic simulation, which is recently developed to actually study turbulence in 3D geometry. And then because like since my master thesis is around 6 months, so I can't able to simulate like ITGs, ETGs, and temps, like all the different kind of turbulence. We choose only one particular type of turbulence which can be realistically simulated during this time period. So we choose ITG turbulence, and then we try to understand how this ITG turbulence is reacting when we apply the Matic perturbations and when apply the Matic perturbations. Meaning we essentially have two Matic equilibrium as input. One Matic equilibrium is without Matic perturbation, another Matic equilibrium is with Matic perturbations. And then we try to simulate the ITG turbulence and try to understand the different characteristics of turbulence, which I will explain later. So, and what's the difference and why there's a difference?
Is everything is crystal clear so far? Would you like to give us a rundown of your most recent results and the problems you'd like to tackle in the future?
Yeah. And but before that, I'd just like to give like what we observe experimentally. Like I said, like there's one more observation that we observed experimentally that is also a key motivation for us. Maybe I can explain that observation that we found, and then it will be better to understand the results. So this is like on the right we have this diagram. Like this is like an experimental observation, like when they did the ELMs suppression as the upgrade. And what they found here is like we have this axis in time. So they applied this Matic perturbation and the ELMs are suppressed. Once the ELMs are suppressed, they started to rotate this Matic perturbation in the toroidal direction. So, and then they measured the density fluctuation at one particular point at the plasma edge. So this basically, this time units, 3 to 7 seconds, can basically be translated into a toroidal angle, because since the Matic perturbation is rotated in toroidal direction. So what they found here is when they rotated, or I can say, see the first figure on the top, we can see it's the displacement of the flux surface due to the application of Matic perturbation. What happening is that the plasma's Matic flux surfaces, there's a deformation. So there's some asymmetry in density, asymmetry in Matic flux surface. And then next thing is there's a corresponding asymmetry in density fluctuation, which is found when we are actually going from a flux surface, which is from the like a crest of the flux surface to the trough of the first flux surface. There's some asymmetry. There's a decrease in density fluctuation. So what they found here is when we apply this Matic perturbation, there is some asymmetry is created in the toroidal direction. So why this asymmetry is causing, like which type of turbulence is causing this asymmetry, is another important question. So okay, so basically we have these two things.
Francis,
First,
if I may interrupt you, could you maybe come back to the previous slide and explain exactly what, well, not exactly, but maybe more simply what we're seeing on the plots, because to me it was not.
Okay, so what's the aim is to measure the density fluctuations along the toroidal plane. So that's the aim. So what they want to find is whether there's an asymmetry in density fluctuation when we measure it in toroidally in a different angle. For example, experimentally it's difficult to measure at all toroidal points in an tokamak. So what they do is they measure at only one particular point in a toroidal location, and then instead of moving the diagnostic toroidally, they move the Matic perturbation, which is causing this density fluctuations. So they are rotating the Matic field caused due to the perturbation, like external coils. And
they
that is
rotate the magnetic field, like they rotate in the toroidal direction.
Yeah, they're rotating in the alpha toroidal direction. Yeah, exactly.
Okay.
And they're measuring at one particular point. So this is equivalent to measuring a different toroidal position in a single time interval.
Okay, so the time axis is also corresponds to the toroidal axis.
Yeah, exactly.
Okay. Okay, thank you.
So, and they found there's some asymmetry in toroidal direction. So this is like the second sub motivation.
And
So
how do they know that? How can they cross-check that the plasma is effectively moving and that the whole structure, with all the macro and micro turbulence, is moving together with it as they create this rotation?
so we know like tokamaks have this like shouldn't have any tokamak like phi dependency because the toroidal direction should be symmetric, phi symmetric. So so if you measure any fluctuation in density at phi equal to 0, the same density fluctuation should be the same at phi equal to some 40 degrees, right? Because there should be any asymmetric anything fluctuation because tokamaks are generally phi symmetric. But now we are applying a matic perturbation which breaks this symmetry. Now the plasma is no more like it has some phi dependence, and that's the thing we are seeing here, where we
Yeah.
see like there's a fluctuation higher at t equal to 3, and then fluctuation like density fluctuation is lowering at 4.5.
Yeah,
So which
I
means
understand, but I guess my question is just one step before that. How do they actually verify that the plasma actually, the entire torus actually rotated?
it's
As
not
they,
plasma is rotated, it's just the magnetic perturbation is rotating. Like there's a field, the magnetic perturbation field is rotated. It's not the plasma which is rotated.
oh, so they have antennas all around the vessel to create the magnetic perturbation, and they just put it somewhere else.
Yeah, they somehow change the configuration, like they change the current through the coil such that it rotates. The
Ah,
magnetic,
okay.
the
Okay.
rotating means there's some maxima minima for the field that is created, and this maxima minima just travels in alpha direction.
Okay.
Oh, in the
Now
toroidal
that
direction,
makes
yeah.
more sense.
Yeah.
Yeah. Thanks.
Yeah. So okay, so basically we like these are the two questions. The first question is the major thing that we observe in almost all ELMs experiments. The second thing is it's also observed. It's like a sub motivation for this. So what I did in during this thesis is, as I said, like I used this tool Gene 3D to understand the turbulence dynamics. So I started with the small physics, which is to study only ITGs, and then in the future I can add more physics. So, so what are three things I studied with this during this master thesis is, first thing is we did some linear simulations and studied how the linear characteristics of the turbulence is changing for the no magnetic perturbation case and when we apply the magnetic perturbations. And similarly, we also studied how the nonlinear physics is also changing between the two cases. And then finally, we also try to understand whether some spatial asymmetry in density fluctuation because of ITG turbulence, because we observed that there's some asymmetry in density fluctuation in experiments, but we also know whether this is caused due to ITGs. So we in simulation we just wanted to understand whether ITGs are causing this asymmetry in density fluctuation. If they are causing, whether they follow the normal curvature, because ITGs are tends to localize in the bird curvature region, where the normal curvature is negative maximum. So these are three questions we try to understand. So this is about the tool characteristics. So I think I can skip this one. But this is like an important slide because so again data needs two inputs. One is the profiles of temperature and density, and next thing is the equilibrium. Equilibrium is constructed by using IDMHD, we code VMAC. So we know the equilibrium will be one with the plasma with matic perturbation, and the profiles will be the temperature and density profile before ELM suppression, which means the H mode profiles, we can say. So we just took this H mode profiles of temperature and density as an input, and then we kept the profiles same for both the cases, for both the equilibriums of with and without matic perturbation, and we just give this as an input. And we calculate the whole plasma whole as this upgrade tokamak. So what we did is we just choose some particular points, like we choose only some particular radial points that we found to be significant. So essentially we took 0.7 and then 0.8 and then 0.9 instead of simulating the whole mission, because we basically did this three positions and then we simulated for both the cases. So the result will be basically constituted on this particular three positions. So I'll just look into the okay, so let's look into the Linnaeus results. So this is for the position 0.7, and then these are the two cases. So what we can see here is this is the mode structure of the turbulence, ITG turbulence, linearly. As we can see, it is concentrated seeing the bird curvature region. Like bird curvature region is it's theta equal to 0. So what it's exactly doing is it's localizing in this particular region, and it's the same for the with matic perturbation cases. So linearly we can't find any difference in the mode structure for the ITG turbulence for both the cases for this at this particular radial position 0.7. And then we also calculated like different parameters like growth rate. Oh, my voice is off.
No, yeah. But somehow I still see your video, but I just couldn't hear you.
Oh, you can see my slides properly.
I do see the slides. I
But
also see your video. I do not. I could not hear you so well.
okay, so maybe I can just give like, did you understand like from which point did you understand this things?
I think this is the last point where I could. I don't know about Danielle and Katia, but yeah, this is somewhat the last slide that I heard.
Like, okay, so what next further observation what we did actually here is we actually studied this growth rate of turbulence, and then we also compared the wave number of the turbulence. So the growth rate essentially means it tells how fast the turbulence is growing linearly. So as we can see for the location 0.7 and 0.8, there's not much increase in the growth rate when the matic perturbation is applied. But for the position 0.9, we can see there's some 20% increase in matic perturbation, which essentially means as we move closer to the plasma edge, where we can effectively see this matic perturbation effect happening, we can see there's a change in the growth rate. Similar thing can also be seen in the wave number, where there's no much difference for 0.7 and 0.8, but 0.9 shows increase in wave number. So this are the observation one. So to summarize, we can see this the mode rate seems to be changing very much for the 0.9 simulation, and similarly the wave number. So next thing is we also did the linear nonlinear simulation to see how the heat flux is actually changing, like heat flux actually. We did do the see here this increase in heat flux when the magnetic perturbation is applied, which means for the magnetic perturbation case, there's an increase in heat flux. So this is the one observation that we found. And then we did some further analysis to understand why this is happening. So maybe I can keep that for the future questions. So this, so for the results, these are the key results we actually observed: linearly and non-linearly. So what we can, like, do you want to continue about explaining why there's a difference in heat flux, or do you have any further questions?
Maybe we could have a few questions from Danielle or Katya, if you're in. If you don't have audio, you're most welcome to type in the chat, and I will read out the question.
Okay, where is the chat box? Here.
So if there are no questions for now, maybe you could tell us why this matters to you, what problem you want to eventually tackle with this, what you want to grow this work into.
Yeah, so okay, I can show that one. Okay, so as I said, like, there are two questions we actually motivated to, like, in the start, right? To understand the density pump out, and then what, like, how can quantitatively predict this density pump by understanding the turbulence behind it. So during a master thesis, since it's difficult to simulate the ITG turbulence with kinetic electrons, like we can simulate ITG turbulence with kinetic electrons and without kinetic electrons. So the kinetic electrons are needed to understand this density pump out mechanism caused due to ITG. So I didn't actually study this density pump out mechanism during the master thesis. So in the future, what they can do is they can actually simulate with an experimental profile. Since I have used only analytical profiles, again, to virtually create an increase in ITG turbulence. Because for the experimental profile, when we simulated, there's no ITG turbulence actually. So we artificially created ITG turbulence by changing the experimental profile. So next major step would be to simulate with a realistic profile, and not only considering ITGs, but also considering different other instabilities along with kinetic electrons. And then we also did consider the neoclassical radial algebra, which can play a major role in turbulence stabilization, especially in the edge. So this also we didn't consider. So we can also include this effect. And then, as I said, we can treat both this as a kinetic species, a gyrokinetic species, to have this density pump out quantitatively predicted. And then finally, there are different kinds of turbulence which comes under this electromagnetic turbulence. Right? We can also something those things.
So you would like to contribute to the gene code by adding resets of physics, gradually adding these elements.
Exactly. So the thing is, now we have the tool. Now next thing is we have to need a time to add all these effects to have this realistic goal of studying this density pump and then density, asymmetry and density fluctuations.
Yeah, and that's great. Why do you think that Gene 3D will eventually be a better code than others? What makes you want to work with this code in particular rather than the others you mentioned?
Okay, so as I said earlier, like Gene 3D is capable of simulating like 3D geometries, but I don't think it's technically better than other like there are different codes like XGC by Princeton. It's also like better, but since I was in Max Planck and they use Gene, so I have to use Gene 3D. So to be in a short way, I can say like all the kinetic codes that are developed around the world can essentially have their pros and cons. So I don't think Gene 3D it's not like a single code that is better than others.
And what would be the major pros and cons of Gene 3D?
Major
pros and cons. You mentioned pros and cons for every code around the world, yes, but
yeah. So for Gene 3D, I can say, for example, I can say for Gene 3D, it can simulate electromagnetic turbulence. It can only simulate only electrostatic turbulence. And then there's one more thing that we need to optimize Gene 3D. For example, Gene 3D can run electrostatic turbulence in a 3D geometry. But how much time it takes to run a particular simulation when compared to similar kind of kinetic code is it's not good. So you have to optimize Gene 3D numerically to make it better. So that's one thing. And next thing is we have to add this electromagnetic feature into the Gene 3D code. And there's also some assumptions that we make in the equations that we implement. So these assumptions can also needs to be relaxed. So I don't want, because some codes consider this assumption, some code ignore this assumption just to have this numerical optimization, like numerically to have a better to run faster, to make the code run faster. So there are also like some assumptions that we make in the code, but this assumption can be relaxed depending on the problem that we solve.
What about major advantages?
Okay, so major advantages, I can't say currently about Gene 3D because Gene 3D is very new, but Gene is very well benchmarked and it's very well optimized, and it can also simulate electromagnetic and electrostatic. So it can quite do major things to study any tokamak related turbulence. So it can be used to study, for example, last talk from Davide. So he was in the Asymmetry side. There was a similar guy in our group, like in the theory department, who is also using the Gene to study I modes. So basically, Gene is used all over the world because it's been there for quite a long time and it's well benchmarked, and it doesn't have any numerical instability. So, and it's the physics results or the output that it gives is consistent with Asymmetry. So it's a well benchmarked code actually, which explains the physics.
Gotcha. Thanks. Are there further questions from the audience? If you, while we gradually move into Q&A, I will make available a survey that we would most appreciate you to fill, mainly for the speaker to get some feedback from his audience, but also for us as a platform to be able to improve this experience for us all. So if you can just take 5 minutes and fill in that survey, would be most appreciated. The survey will also be available on our social media later. And now we will take questions, if there are any. Thank you for taking the time to joining us today. And if there are no more questions, then we're looking forward to see you all again for our next talk on the 20th. Stay tuned to our channels, and the recordings of this video will also be made available.
Yeah. Thanks everybody for attending my talk, and especially I have to thank Alexis for hosting the talk. Yeah. So see you guys later.